flipped classroom video for Maths AS Unit 1, some exact trigonometric values. First of all, we'll look at multiples of 90 degrees. So if we use the graphs, and these values all follow from having a good knowledge of the trigonometrical graphs, and that in turn comes from a good knowledge of the use of the unit circle to define trigonometric functions. So you need to make sure you're comfortable sketching these curves. So if we look at sine first, sine starts when the angle is 0, sine is 0. When the angle is 90, sine has risen up to 1. By the time we get to 180, it's fallen back down to 0, carries on falling and hits -1 at 270 degrees, and then is back to 0 at 360. For cos, it starts at 1, falls to 0 for 90 degrees, carries on falling down to -1 for 180 degrees, and then climbs back up to hit 0 at 270 and 1 at 360 degrees. For the tangent, at 0 the tangent is 0, and then it rises up, approaching or heading towards infinity at 90 degrees, and then just after 90 degrees it comes up from -infinity, hits 0 at 180 degrees and heads off to infinity again at 270 degrees. Just after 270 it does the same as what it did after 90 degrees and climbs back up and hitting 0 again at 360 degrees. And there's lots of relationships which you'll have seen if you've watched our previous video on defining the trigonometrical functions using the unit circle, or you'll have looked at this in class and will continue to do so. But just one thing I'd like to point out here is that this does repeat every 360 degrees. So if we have any multiple of 360 plus 90, it will have the same values as all of them. Sine, cos and tan will have the same value as they do at 90. Similarly, for 360 times anything, any whole number that is, n generally stands for whole numbers of course, so 360n plus 180 will have the same values as 180. If we add 270 to 360n, we get the same values as we do at 270. And then for 360 times n, we get the same values as we do at 360, which of course are the same values we get at 0. So these you need to know, or you at least need to be able to sketch the curves so that you can bring them back to mind if required. Okay, so we're going to look at half a right angle. So that's of course 45 degrees, and we can use a particular triangle to work out the trig functions for this. So that triangle looks like this. So it's a 45 degree right angle triangle. So both the other angles are 45 degrees of course to add up to 90, and we are arbitrarily calling the two shorter sides 1. They must be the same through symmetry, and the hypotenuse we've labelled as h. So using Pythagoras we have h squared equals 1 squared plus 1 squared. That means that h squared is equal to 2, and therefore h is the square root of 2. And now we've established that, we can just read off the triangle, and we can say that sine 45 is 1 over root 2, cos 45 is 1 over root 2, obviously sine 45 being opposite over the hypotenuse and cos 45 being the adjacent over the hypotenuse, and tan 45 is opposite over adjacent, so it's just 1 over 1. And we can simplify those. So 1 over root 2, you may know from your work on surds, if we times the top and bottom by root 2, then we will end up with root 2 over 2. The root 2 times root 2 on the bottom is root 2 squared, which is of course 2. The same job can be done with cos 45 to get root 2 over 2. And then possibly the simplest thing you'll see on any of these videos, 1 divided by 1 is of course 1. So that's tan 45 equals 1. We can also look at a third of a right angle, and in fact a third of a right angle is 30 degrees, and we can also find the trig functions for 2/3, which is 60 degrees. And again we use a particular triangle to find these. And the triangle we use, you won't be surprised, is an equilateral triangle, because we have 60 degree angles there already. and this time we call the length of the sides 2. And the reason for that is, you'll see, the first thing we do with that triangle is we drop a vertical down from the top. This is a vertical that's at right angles to the base. Now that of course splits the base exactly in two because it's all symmetrical. So now from the corner to where the drop down line hits the base we have just 1, and that sloping side is still 2, and we can work out what the length of the drop down red line is, because we have x squared equals 2 squared take away 1 squared, which is of course 4 take away 1, which is 3, and therefore this height, which I've called x for some reason, is root 3, and we can pop that onto the diagram. So now if we think of that triangle formed by the left hand slope of the original triangle, half the base, and this red dotted vertical line, then we can find our cos, sine and tan for 30 and 60. The angle at the top there is of course exactly half of 60 because we've split the triangle in half, so that's 30, and the angle at the bottom is still 60, but I've added it in red so you can see the whole triangle. So sine of 30 is the opposite of 30 over the hypotenuse, so that's 1 over 2. Cos of 30 is the adjacent to the angle 30, so that's root 3 over the hypotenuse, which is 2. And the tangent is the opposite 1 over the adjacent root 3. For 60 degrees we look at the triangle the other way around, so we're now using the 60 degree angle at the bottom, so the opposite to that one is root 3 and the hypotenuse is still 2, so that's sine 60 is root 3 over 2. Cos 60 is the adjacent to the 60, which is 1 over the hypotenuse, which is 2, so that gives us a half, and tan 60 is the opposite to our 60 degree angle, which is root 3 over the adjacent, which is 1. And there's a little bit of tidying up we can do here. With tan 30 we can do a similar job to what we did with sine and cos of 45. So if we times the top and bottom by root 3 we end up with root 3 over 3, and for the tan 60 we can write it without the dividing by 1 of course. So we'll just finish this little video by having a look at an interesting set of results. So we'll put all the values that we've found in the video into this table. So for sine we had 0, of course, for 0 degrees, a half for 30, root 2 over 2 for 45, root 3 over 2 for 60, and 1 for 90. For cos, because of the symmetries on the trig graphs and of the trig functions, that's the same values in reverse. So it starts at 1 and goes down to 0. And then for tan we've got 0 at 0, we have root 3 over 3 at 30, 1 at 45, root 3 at 60, and then infinity of course at 90. Now we can play with those numbers. They don't look to give an obvious pattern as they're written, but we can play around with them. So we'll redraw our table, and this time we're going to write 0 as the square root of 0 over 2. Now the square root of 0 is 0, 0 divided by 2 is 0, so this is the same as the value in the top table. A half we're going to write as root 1 over 2, and root 1 is 1, so that's still the same as a half. The next two we just copy down from above, so we have root 2 over 2, root 3 over 2, and then for 1 we write it as root 4 over 2. Root 4 is 2, 2 divided by 2 is 1, so this still matches that value, and now you can see this rather great pattern. So we have root 0 over 2, root 1 over 2, root 2 over 2, root 3 over 2, root 4 over 2. And this is included really as an interesting pattern or an interesting set of results, as it says on the screen, but it's another way of perhaps remembering them as well. Cos, of course, will be the reverse of that, as it was in the above table. For tan, we get a slightly different pattern. So for 0, we're going to write that as root 0 over root 4. For 30 degrees, we write that as root 1 over root 3. Now if you remember, the root 3 over 3 came from 1 over root 3, and 1 over root 3 is the same as root 1 over root 3, of course. For 1, we're going to write that as root 2 over root 2, which is clearly 1. For 60 degrees, or the root 3 value we have above, we write that as root 3 over root 1, and then we have our infinity. But the pattern for the tangent is we have root 0 over root 4, then the top goes up and the bottom goes down, so we have root 1 over root 3, root 2 over root 2, root 3 over root 1, and if we were to continue that, we would have root 4 over root 0, which we're not allowed to do because we're not allowed to divide by 0, but if we let the bottom of a fraction approach 0, we do indeed end up at infinity. So in a certain sense, that pattern could continue into that bottom right cell on the table. So there we are, just an interesting set of results to finish with, and that's the end of this video.